Going on now to topic 5 of chapter 1, dealing with exponents and radicals. So, let's take a look at that. Integer exponents. That is, exponents that are either a whole number or an integer. Now, in section 1.2, we talked about if our bases were the same, and we would multiply these variables just by adding the exponents. Now, if we're going to divide, here we have 6 to the 5th power, 6 to the 2nd power, and written out, it looks like this. Let's see what we can do here. Well, there's a 6 over 6. That cancels out. That's a 1. We have 6 over 6. That cancels out. That's another 1. And we're left with how many 6s? 3. So this is 6 to the 3rd power. Now, we could do that all the time, or we could do what I had said before, and I knew we were going to cover it later. We can take the exponent, cross the division bar with it. Up here it changes its sign. That is, subtract, and we get 6 to the 3rd power. And that basically is the rule we're going to be following here. So the rule, once again, is the exponent comes up, crosses the division bar, and we just subtract it. And as long as we want to make positive numbers for exponents, we would always subtract the smaller from the larger. So again, we're going to bring the 4 up across the division bar, subtract it, 5 to the 3rd. Subtract the 5 from the 10, and get this in parentheses now. That's our base to the 5th power. And the same thing holds. If our base is the same, we just raise the exponent above the division bar, change its sign. Now, another rule dealing with exponents is products, which is a times b, that are being raised to a power. Now, in a sense, let me write this out for you so you see it. We have a, b to the nth power. Now, there is an exponent by the a that we don't write. It's a 1. So actually, then we're raising this 1 to the nth power, and we multiply here. So this becomes a to the nth, b to the nth, with no parentheses. So for something like this, 2x to the 5th, the quantity to the 5th, again, there's a 1 there and a 1 there. So this becomes 2 to the 5th, x to the 5th. And 2 to the 5th is 32. X to the 5th is what they have here. And it applies if you have a fraction as well, that there's a 1 there, becomes a to the nth, b to the nth. Okay. Now we'll just review these using what's in the book there. So it's going to be 5 to the third, which is 125, and then y to the third, y to the third. Now here we're going to multiply 2 to the times 4 is c to the 8th, d to the 12th. This is sort of an intermediate step. You do that mentally. And this is x to the 6th. 2 to the 6th is 64. And this will be a 12, and this will be a 9. Okay. Again, pretty straightforward. And there's another example that they're showing. Let's look at that now. This will have to be done in 2 stages, I'm pretty sure. So this is going to be r s to the 6th, and this will be r to the 8th. Now this becomes r to the 6th, s to the 6th, r to the 8th. Well, r to the s to the 6th here. Where did I get that from? Okay, so r to the 6th, s to the 6th, over r to the 8th. All right, now we know we can do some canceling here. We want to keep our exponents positive. So I'm going to bring the 6 down, subtract it from the 8. And this just stays on top. There we go. Now we're going to take a look at what is called negative exponents. So here we have 3 to the 2nd, and then 3 to the 4th. Well, again, if we bring this 4 up, this will become a negative 4. So we then have 3 to the negative 2. Now, again, we often don't want to have negative exponents. So if we do it the other way, 3 to the 2nd, 3 to the 4th, bring this down here and subtract it. And remember there's a times 1 there. This is going to be 1 over 3 to the 2nd in the denominator. So when we look at our negative exponents, 3 to the negative 2 is the same as 1 over 3 to the 2nd. So all we're doing there is taking this negative exponent along with its base, leaving the one that's not written up there, bringing it down, and these are equivalent. And again, they're showing you the work. So as we look at the rule for it, a to the negative n becomes just 1 over, bringing this down to the denominator, becomes a positive. And here are a few examples. 3 to the negative 2 is 1 over 3 to the 2nd. Simplified is 1 over 9. X to the negative 1 is just 1 over x to the 1st. We don't write the 1. Now, this next one is sort of interesting. I'm going to show you a little shortcut for it. When you have a fraction, and it's to a negative exponent, all that is equal to is you take the reciprocal of this, which is 4 over 3, and that then becomes a positive exponent, which is just 4/3. So anytime you have something that's just to a -1, flip it and it's to a +1, which is just the reciprocal of the number. Here this is 1 over 5 to the 4th, which is this. Now, this is sort of interesting, because what is the base here? See, that negative is up outside of the base. The base is only this. So the negative stays there. That's, in a sense, a -1 over 4 to the 2nd, which is a -1/16. So this one's a little tricky, because this negative exponent only applies to the base and not the negative sign. Okay. So in this next part here, they're showing you that, in a sense, this goes down there. And again, the shortcut of it gets a little complicated this way. If you have a fraction that is to a negative exponent, just flip it and it's to the 4th power. And then whatever these are. If you simplify this, 3 to the 4th is 81. 2 to the 4th is 16. But you started off with this, and you flip it, and then it just becomes this, with a positive exponent, and then 3 to the 4th, 2 to the 4th. Okay? And here they're showing you the inversion property. That a fraction, if you take its reciprocal, the negative exponent becomes positive. And they give you a few examples, and you'll be having some too. Okay, we're now getting ready to look at roots and rational exponents. These are exponents that, instead of being whole numbers, may be fractions. But some background: if we take the 3rd root of 8, that's a 2. And if you take 2 to the 3rd power, that's 8. So again, we're going to look at rational exponents that are going to relate to roots, and roots are radical expressions. This sign here is a radical sign. The number that fits in the notch is called the index number, and then what's under the radical sign is called the radicand. So we'll be doing some work with this as we go on. So let's look at some background here. If we had a to the 1/2 power, which is, again, this is the exponent, but it's a fractional exponent, times a to the 1/2, we add that together and we just get a to the 1st. Now, there is a relationship that we'll be building as we go on. And if we say a to the 1 over n, that this is a fractional exponential form, this is related to a radical. Now the a, which was the base, now becomes the radicand. The denominator of our fractional exponent, this n, the denominator, becomes our index number, and the numerator, which is the exponent, just goes right there. So if we had a to the 1/2 power, that would be equivalent to radicand a, index number 2, to the 1st power. Now we never write a 2 in this little notch. If something is a 2, we just don't write it. Automatically, if there's no number there, it's a 2. So a to the 1/2 power is equivalent to the square root of a. Okay, let's look at some of these now. So we have 36 to the 1/2 power is the square root of 36, which is 6. And we can just look at this. Square root of 100 is 10. Now, keep in mind, this is a negative 225 to the 1/2 power. So this is a negative square root of 225. Now the square root of 225 happens to be 15. Then we apply the negative sign. So this is a negative 15 right there. Now letter D is the 4th root of 625. Because the index number is 4, 1, and that is a perfect 4th. That's going to be 25. Well, let's change that. That's going to be 5. Yeah, because 25 squared is 25. So I didn't take it down enough here. Got carried away here. Okay, now, an interesting thing, the 4th root of a negative 1296. Anytime your index number is even and you have a negative sign under the radical, that's not possible. So there is no real number solution if you have an even index number. Since you have, for instance, the square root of negative 4, are there any two numbers that are exactly the same that you can multiply to get a negative 4? And the answer is no. You might say 2 times 2, that's a positive 4. And negative 2 times a negative 2, that's a positive 4. So there are no two numbers that are exactly the same that will give you a negative 4. So we say that is not a real number. Now, if we get a negative under the radical sign, and I think I can clear this up here to get some room, such as the 3rd root of a negative 27. That's this one. I'm changing it from its fractional exponential form to its equivalent radical form. Now, since it's an odd root, we are allowed to have a negative, because this answer happens to be a negative 3. If you take a negative 3 and cube it, you get a negative 27. But that doesn't go there. So, negative 27, and notice this is in a parenthesis. It's including the negative. Now, this is a fifth root of a negative 32. Again, if it's odd index number, that's fine. If our denominators are odd, it's okay to have a negative. This is going to be a negative 2. Because negative 2 to the fifth power is a negative 32. Okay. Some background here. And it's just showing us that this will work. Okay. Let's see what they want us to do here. Now, again, these are all examples of exponential fractions, and they are related to radicals. And if you put them in their radical form, they're very easy to work. So again, let's put a radical sign by each of them. We're going to convert these to their radical form. Now the denominators are the index number. The base is the radicand. And these exponents now we're going to put out here. And now we actually do the calculation. Third root of 27 is 3. 3 squared is 9. Fifth root of 32 is 5. 5 to the... Let's try that again. Fifth root of 32 is 2. 2 to the second power is 4. Third root of 64 is 4. 4 to the fourth power is 256. Now the square root, and again we don't write the 2 there. The square root of 25 is 5. 5 to the third power is 125. Now they're using another form of calculation, which is good too. They're saying the third root of 27, I guess, is 3. 3 to the second. But again, I like to do it this way. So if the fraction, you have a fractional exponent, the denominator is your index number. The base is the radicand, and then you raise it to that power. And that's what we've done. And they're giving us some error messages sometimes if you're using your calculator for this. Let's go on and see where we are here. So here's a little chart. If I were you, I'd copy this in my notes. This gives a summation of all that we've done. And now the proof of the pudding is whether we can do some of these. So let me write some of them up and go over them with you. We'll do a few before they get too complicated. So here we're going to just add the exponents. This gives you 7 Negative 4, 6 to the second, which is 49. And that checks. Now here to add our exponents, we have to have common denominators. So this is going to be 2 times, and what's our common denominator here? It's going to be a 12. So 4 times 3, this is going to be 8. This is going to be 4 times 3 is 3. So 5 times 2 is 10. 8 and 3 is x to the 11 twelfths. And I don't like the way they're writing this, but I guess it's okay. Here we're just going to move the negative 6 up. Here it becomes a positive. So 14 plus 6 gives us this. And for letter D, let me set that up. Well, we're going to have to move this up. So when we do, what is 5 with a denominator of 3? Well, 15 thirds, that's 5, and minus 4 thirds. And so we get an answer up in the top of c to the 11 thirds. But in our denominator, we're going to get a 2. And that's where they got this answer. And let me set up E for you. So up in the top here, this is going to be 27. 1/3 plus 5 thirds is going to be 6 thirds, which becomes 2, over 27 to the third. Going to subtract the 2 from the 3 down here, so we get 1 over 27. I think they're doing that down there. Okay, well, not too bad. There it is. All right, and over here we're getting some tedious ones. Let me set that up. So here the rules of signs are the same. Negative times a negative will make this a positive. 3 times 4 is 12 sevenths. So that's pretty straightforward. And let me do B. So one of the things I think is helpful is to put it in a nice fractional form. So here we have a 1 there. So this is going to be 3 to the second power. And then here I can do some canceling, and this becomes m. That goes into there 3 times. So we get m to the 5 thirds there. And I can write it again like I did here. So this will become a 2, and that cancels out. So we get y to the 3 halves. And this 3 to the second will just become a 9 here. And that looks like our answer. Okay. Again, I like to write it this way. Writing it with those diagonal lines tend to be confusing. All right, let's set up letter C. So here we're just distributing, and this will become m. Nothing cancels out. We're going to add these together. This will be 9 thirds. Because we're not multiplying, we're adding exponents here. And this will be plus 2 m to the 3 thirds, So this becomes m to the third plus 2m to the first, and we don't write the 1. And that's what we have. Okay. Well, it's nice to have it all written up there as well as backup. And let's see what we're doing here. All right, this looks like it's a little long, but these, I think, are pretty clear. Again, we're not going to try to do every single one, but I think a to the negative 1 here at the end. Keep in mind this is just another way of writing 1 over a plus 1 over b. So our common denominator here would be ab. So we would need to multiply this one by b over b, and this one by a over a. This is a 1. This is a 1. We now have our common denominator, so it's going to be b plus a. Now, that's what they have. Okay. I'm assuming you'll get these from the others. If you need help, check with your tutors and instructors here. Wanted to try to keep these to about 10 minutes long here. And here's a little example. Again, if you put that into your calculator, you can get a good result. Now, interestingly, I think we've done this already, that the radical form is equal to its fractional exponential form. So I think we've done these. Good. And a few more topics here. Let me go over some of this. Now, when you see something like this, the square root of x squared, you would think that that would be an x. Because if you recall, there's an index number of 2 there. Take away the radical sign, put it in this form, and this becomes a 1, and you get an x. But keep in mind, this could have been, if you had here, let's say a 4, 2 squared could have been a negative 2 squared, negative 2 squared, or 2 squared. Both of these are a 4. To ensure that, they want you to write it in its absolute form, keeping in mind there could have been a negative that you squared. And that's what they're illustrating here. All right, let's see. All right, they're putting a lot in this. Now, when we're dealing with radicals, I'll give you some general background on this. If we say we have the square root of 8. Now, if we were asked to simplify that, I've always told students to see, by setting up 2 radical signs, if you can find a perfect square factor that 8 might have, which is 4, and you're left with a 2. Then you can take the square root of 4, get 2, and what's left over is the square root of 2. So 8 in the future, square root of 8 is always 2, the square root of 2. Now, suppose you had something like this in example 1. And let's see what we can do here. 6, we know, is 2 times 3 is 6 times 9. So actually this is a 6. So underneath our radical sign, in a sense, we have 6 here and 6 there. That would be 36. 6 times 6 is 36. And that's a perfect square. And we have 9 is a perfect square. So the perfect square of 36 is 6. The square root of 9 is 3. And they're saying that gives you an 18. So if you multiply your radicands and get one big one, this happens to be a perfect square. And they're showing you that way here too. Now another way to do this one is you take the square root of 7 and separate it, square root of 64. Square root of 64 is 8. So you have the square root of 7 over 8. Now for letter C, we have, let's see, the square root of 25 times the square root of 3 minus the square root of 4 times the square root of 3. I'm just teasing these apart into perfect square factors. So this now becomes 5, the square root of 3, minus 2, the square root of 3. And in a sense, you can consider these as variables. We're just going to deal with our numerical front of these. So 5 minus 2 is 3, the square root of 3, which is what they have right there. And this is a long lesson. Okay, we're going to do some foiling now. Wow. So let's do some foiling here. This times this is going to be 2 times 8 is 16. Square root of 16 is 4. Now my outers is a negative 5, the square root of 2. My inners is plus 3. Now we said the square root of 8 was actually the square root of 2 times the square root of 4 times the square root of 2. So this is going to be 6, the square root of 2. And then our last is a negative 15. So we have here a negative 4 and a negative 15 gives us a negative 11. Then we have a negative 5 and a 6 just gives us a plus 1 that we don't write, the square root of 2. And there that is. Now in letter B, these are conjugates that we mentioned a long time ago. So when we deal with conjugates like this, the middle terms cancel out. So this is the square root of 49, which is 7. This is the square root of 100, which is 10. So this ends up being a negative 3. So not too bad. But again, lots of stuff, and we are approaching 40 minutes here. Wow. This was a long section here. I think we're just about finished here. Now they want us to rationalize denominators. So let's pick a number that will make this a 3, let's say. So we can multiply this fraction by 1, and I'm going to use the square root of 3 over the square root of 3. This is a 1. So my denominator now becomes a 3. And my numerator becomes 3, the square root of 3. And I have rationalized, well, let me put a 4 there. Oh, I'm getting a little tired here. So 4, the square root of 3. There we go. Okay, now for this one, whenever we're going to rationalize the denominator, and we have a sort of a binomial there, we use the conjugate. So this will be 3 plus the square root of 2. 3 plus the square root of 2. Remember, this is a 1. Anything divided by itself, except 0, is a 1. So our numerator now becomes 3 plus the square root of 2. And our denominator we just FOIL, 9 minus 2, which becomes a 7. So we have 3 plus the square root of 2 over 7. Wow. Now when we're asked to rationalize the numerator, it's the very same process, but now we have to have 1 for our numerator that will be its conjugate, and they're showing that there. And then they show the work where we FOIL our denominator and our numerator now becomes rationalized. Wow, lots of stuff. Well, hopefully this is helpful to you. It was a little long.